Thank you for a nice introduction. So this is a work based on our joint work with Gleb Kovachev, and it's a great pleasure to be here in the place where a lot of great research on high-dimensional expanders has been conducted. And so let me start from something much more simple, from classical LDPC codes. These are kind of very standard definitions. So a classical LDPC code is just a classical code defined by sparse parity check metrics. Yes, and as usual, we have Hamming metric, we have minimal distance, so we have, and the restriction here that, so what I mean by low density metrics, I mean that all rows, and I also assume that all columns also has weight that is limited. LDPC codes can be very naturally represented by what is called Tanner graph. So it's a bipartite graph where we have two parts. One corresponds to bits and one corresponds to checks. These codes were introduced by Robert Gallagher in the 60s, and nowadays they're used almost everywhere. It is known that, so already in the 60s, Gallagher managed to show that there exist good families of LDPC codes. And by good, I mean that their parameters, main parameters, are asymptotically good. So the dimension grows linearly and the distance grows linearly. And then, as many of you, I expect that many of you very well aware of, there was a paper sequence of work by Sipser-Spielman and then Spielman that showed that in fact you can not only have good families of LDPC codes, but you can also construct them very explicitly, and you also have as a bonus linear time decoding and encoding. So here I would like to show you what are the standard ways how LDPC codes are constructed in practice. And so for this I need this notion from graph theory that is usually called lift, and if you're a topologist, maybe you know it under the name L-fold covering. We have some graph, and we have some set F of size L, which is usually called fiber. And in most cases, this fiber is just some group. And in fact, in most applications, this group is just cyclic group. Now we assign to each edge of the graph some permutation, some element of this symmetric group. And using these assignments, and in different communities, these assignments are called differently. So sometimes they're called lifting maps, sometimes voltage assignments, and sometimes are just assignments for labeling. So, and using this labeling, so we can obtain L times larger graph in a very straightforward manner. So since we have here a symmetric group, so we assign a permutation. So it's just a permutation, and we use this permutation to connect these edges, and here is some example. And so since LDPC codes are defined using graphs, so we can easily apply this idea to codes as well. So if we start from this very small graph, so we can obtain, for example, three times larger graph. Yes, if we use, so in this case I use just cyclic group of order 3, and here these labelings are just shifts, but in general, so they are just so by analogy, so we can use any group, and yes, and we just instead of shifts, so we just perform multiplication in this group. And why this? What we obtain is usually called lifted code. And this lifted code, it can be very naturally represented by a matrix in which elements are elements of the ring, not of the field, but of the ring. And this ring, what is known as group algebra. So group algebra is just like polynomials, but where instead of intermediate variables, we have group elements, and multiplication is exactly the same as in the group. And so of course we can also replace all these rings elements by binary submatrices, and in this way, so we get this large, in this case 3 times larger parity check matrix. Okay, so why this idea is very important, is so often used in practical applications. So there are many reasons for this. So first of all, if you see, so here from one small graph, one small code, we obtain infinite number of larger codes of different sizes. And what is very cool, that the rates of all the lifted codes is at least as good as for the base code. And even more importantly, so if we use non-abelian lifts, so elements from, for example, symmetric group, so we can also have linear time distance. So as you can see, yes, the number of bits and the number of checks also grows linearly. So we have for free linear growth of dimension, but we also can have, as we will see, linear time growth of the distance, which is really cool. And another important property of these codes is that you can predict the performance of this lifted code just by looking at this small base code. And so the idea that is used here, so we construct a universal cover of this graph, and this universal cover is a tree, and it turns out that the standard decoding algorithm that is used to decode LDPC code, that is called belief propagation, so we can estimate its performance very accurately if we consider graphs. So and then, so we since this lifts the kind of approximation of this universal cover, yes, so we can use this knowledge to predict the performance of the actual finite code, lifted code. And another very important property, which is very useful for practical application, is that these codes comes naturally with parallel processing algorithms, so both for encoding and for decoding. Okay. And now, so here are some examples how we can obtain good classical DPC codes from lifts. So very straightforward ideas. Just for example, if we start from bipartite graph, complete bipartite graph, so we can assign random permutations. And so here I show some example of infinite family of such codes that all have rate at least one third. And so if we assign this permutation randomly, then it was shown that we get good codes. And another idea very similar to this that I will describe in a minute, so it is so-called Zemer codes. So this is a slight variation of the Sipser-Spielman expander codes. And so if you are not familiar with this particular concept, because it's not very common name, so I advise you to check these lectures by Daniel Spielman, where he describes these particular codes and how they are related with the Zemer decoder, which is a special decoder that works very fast and works particularly for these codes. In our paper with Gleb Kulachov in 2020, so we generalized this idea of Zemer codes to arbitrary to lifts of bipartite graphs. So essentially it's the same idea, so but instead of lift of this small graph, which happened to be just a double cover of a Kelly graph, so we suggested to use lifts of more general graphs, yes, and this gives us a way to use this construction in in significantly many scenarios. Okay. Let me first briefly remind you about Sipser-Spielman codes. So Sipser-Spielman codes are Tanner codes. So it means that we have a graph and we assign bits to edges. We assign local codes to vertices. And so we typically use some d-regular graphs, delta regular graphs, and what's the main idea behind this Sipser-Spielman codes, that they notice that if we use small set expanders, yes, if this graph is small set expander, and by small set expander I mean that if our set of vertices is sufficiently small, for example, 1% of all the vertices, then we have almost perfect expansion. For example, 99% of all the edges go outside. And so, since it was known that good spectral expanders, for example, Ramanujan graphs, are also good small set ones. So by good I mean that this set grows linearly with the size of the number of vertices, with the size of the graph. So this allowed them to obtain the following theorems. So if we choose local codes which have distance that grows at least as the square root of this delta, the degree of the graph, then you can get asymptotically good classical LDPC codes. Here n is the length of the code, yes, so it's total number of edges, and delta is the degree of this graph, yes, and so the relation is as follows, yes, that delta is a constant, delta is a some maybe small constant. So I mean that, so if you use local codes that have sufficiently large minimal distance. In fact, you can use good codes, yes, as your local code. So it's not required to use such kind of codes. But the idea of Sipser-Spielman also works if your codes are not good. So in this case, you obtain asymptotically good codes. But by n here, I mean, of course, the total number of edges. Okay, but here I assume only small set expansion. So small set expansion. So for very small sets, it's like, so you can get like, you can get arbitrarily close to 100%. Yeah. Okay. So here are some generalization of Zemer codes that I already mentioned. So the original Zemer codes were defined on the lifts of these graphs. And so in our paper, we defined a generalization of this idea, yes, and we also use exactly this idea in our final paper where we show the existence of asymptotically good codes. So here I show you the parity check matrices of Zemer codes, and why they're interesting for us, because these Zemer codes, yes, their parity check matrices can be represented as matrices over a ring, which will be very important in our constructions that I will describe later. And so here is some example. Yes, if you consider a cyclic group, yes, here is just this ring, this group ring is just very standard in classical coding theory ring, yes, that is related to quasi-cyclic codes. And here you can see, so if you apply this idea of Zemer codes to Hamming code, yes, this is a Hamming code, parity check matrix, and you get the following parity check matrix. And this is a polynomial parity check matrix, so each entry is like a polynomial. So what is important, so what we showed in our paper, we showed that if we, to introduce you, so first I need to introduce you this concept that we called alpha-beta expanding. So it's very simple concept that if you apply parity check matrix to a vector that has sufficiently small weight, Hamming weight, then you always get syndrome, which weight grows at least as beta times the weight of this vector. And so we call it alpha beta expanding, and what we showed, and also this also was also shown independently in the paper by Brookman and Eberhard, that if the local code and the dual to the local code, they both have distance that grows at least square root of n, then we have alpha beta expansion for both, for parity check matrix of the code and for transposed version. And this is, in fact, was very important in the context of quantum code. So in quantum codes, we often we need to use some constructions that are kind of symmetric. And this this part was new. Of course, the first part I think was very well known, but the second part was new. And we also made a very simple observation, which is also very well known, that if you take just random matrix, yes, then just applying Gilbert-Parshomov bound, yes, and you know that you can apply Gilbert-Parshomov bound both for generator matrices and parity check matrices, yes, and by using union bound, you immediately get the following result. So it is not a big problem, yes, to have codes that simultaneously have large minimum distance and large minimum distance in their duals. It's very simple. Okay, now let us discuss quantum LDPC codes, but before I discuss them, so let me introduce some important concept from algebraic topology that is called chain complex. So a chain complex is just a sequence of vector spaces such that if we apply two consecutive linear, so it's a sequence of vector spaces and also linear maps between these vector spaces. And if we apply two consecutive linear maps, then we should always get 0. So this is a condition we need to satisfy. And this allows us, in fact, from coding theoretic perspective, the common way is to consider this matrix kind of generator matrix and this matrix kind of parity check matrix. So, and this condition, it just says that the code generated by this generator matrix is subcode of the code that is checked by this parity check matrix. And this allows us, since this code can be different, yes, and this code is called the code of I boundaries, and this is I cycles. And so we can also consider quotients. And these quotients are called in algebraic topology homology groups. And we also can consider the dual notion when we, instead of these parity check matrices, instead of these linear maps, we consider the transposed versions. And we just reverse arrows. And this is something that is called cochain complex. And in this case, we also call it co-boundaries, co-cycles, co-homology groups. So we always add co. And a canonical example of this cochain complex. So if we, for example, consider some torus and we consider its cellulation into squares. So in this case, so we can have these three types of spaces. Yes, it's a linear combination of squares, linear combination of edges, and linear combination of vertices. And we have a very natural map. Yes, that is called boundary map. That sense, if we have a square, so boundary map is just a sum of all these four edges. And exactly the same, yes, if we apply it to edge, then this is just a sum of these two vertices. Okay, so and it is well known, so you can see it from this picture, that the homology group it has dimension 2, and here you can see the representative of this homology of these elements. Yes, so so we have two cycles, big cycles in the torus, and they explain why you have dimension equal to 2. Okay. Now, what about quantum LDPC codes? So, quantum LDPC codes, so in this talk, I will consider only some narrow notion called quantum CSS code. So, a CSS code is a pair of classical LDPC codes, and we have the following relation. So, these two codes are defined by parity check matrices HX and HZ. And we have the following relation. And the reason for this relation is because in quantum case, so we have two types of errors. We have X errors, the standard bit flip errors, and we have also phase flips. And from laws of physics, and so we know that we need to satisfy this condition, yes, to define the correct code. So this is a necessary condition, so this code was correct. And so you can also define the parameters of the code. So it's n is a dimension. So k is a dimension of these quotients. And geometrically, you can consider this as some quotient Hamming space. Yes, so we have binary vectors, and we consider quotients of these vectors, and so we define quotient Hamming matrix. So it's just the distance between two classes, and by considering this quotient Hamming matrix, so we have exactly the same problem, yes, as for the classical LDPC codes, but we just modify the distance. So in the distance of the quantum code, it's defined as a minimum of this dx and dz, and we can use these formulas. And why are these quantum LDPC codes are so important? Because many people believe that we can use these codes to construct future fault-tolerant quantum computers. And so, and the theorems that I'm going to present you today, so that we proved in 2021, that there are good families of quantum LDPC code. Okay, and here I also want to mention that LDPC codes are naturally related to chain complexes. So classical LDPC code can be considered as a chain complex with two terms. Yes, one with bits, one with checks. But quantum LDPC code can be considered as a complex with three terms. Yes, where we have Z checks and X checks, and we also have here qubits. And you can easily verify that this condition that defines CSS code is exactly equivalent to the condition of the chain complex. So, so whenever we have a chain complex, we have qLDPC code. Whenever we have a qLDPC code, we have a chain complex. So those are essentially the same things. And moreover, the distance, yes, that we define, it's dx and dz, is just exactly the quotient Hamming distance applied to homology groups. And so the common way to construct quantum LDPC codes is just to take some interesting topological space, consider it finite simulation, construct the corresponding chain complex, and then by interpreting this chain complex as a graph, this 3-bipartite graph, so we can define quantum LDPC code, which is also can be defined by this 3-partite graph, yes, which is also called Tanner graph of quantum LDPC code. The canonical example of such a code is the so-called Kitaev-Toric code, which is defined by using the simulation of a torus, and I already described this. And so the only thing I want to mention is that the distance corresponds to the systole, to the smallest non-contractible loop. And in this case, if we consider L by L lattice, yes, we have that the minimum distance is equal to L, and the length of the code is equal to 2 by L squared. So you can see that, and the dimension is equal to the homology, so it's equal to 2. It doesn't grow. Unfortunately, it doesn't grow with the size of the lattice. Okay. And here some also, I think, interesting idea. So every quantum LDPC code can also be interpreted as a topological space. So as we already saw, yes, every finite simulation can be converted into quantum LDPC codes, but we can do exactly opposite. So, so the natural question to ask is whether we convert arbitrary quantum LDPC code into some kind of topological space, and the answer to this question, yes. So we can do this if you interpret this Tanner graph as a poset with 3 levels. So this is the largest level, middle level, and the lowest level, and this so these connections they correspond. So we can see this graph as a Hasse diagram of this poset. And if we interpret qLDPC code in this way, so there is a very natural way to assign a simplicial complex to arbitrary qLDPC code. And in fact, if we apply this idea to toric code, we again obtain a toric code, which is also interesting. And we can use this idea. So why I mentioned this idea? Because potentially we can use this idea to construct a lot of new quantum LDPC codes just by considering arbitrary posets. And we know in mathematics there are a lot of different posets, and we can convert them into simplicial complexes, and we can then obtain qLDPC code. And the natural and open problem here, whether we can construct some qLDPC codes of large distances from this. But my today topics is related to with concrete constructions that we call lifted product code. But before I'd like to discuss it, so let me first explain what is tensor product code. So I guess that almost everyone here know what is tensor product code. So this is just a very brief recap of this notion. So here we have 2 codes, A and B, and we define the set of matrices where every column is from code A and every row is from code B. So this is what is usually called tensor product code. And this tensor product code can be very nicely described by its parity check matrices. So if A is a parity check matrix of code A and B parity check matrix of code B, then we can describe these matrices W as by these equations. Yes, if we multiply from the left by the matrix A, so we obtain the syndrome that corresponds to, so this is all the syndromes that corresponds to this horizontal vertical checks. And if we multiply from the right, yes, by transposed version of B, then it means that we apply this matrix to every row, and so we check the code B. And these codes are very nice because they have very, very simple parameters that can be easily calculated. And hypergraph product codes so they are naturally related to this product construction. So here, as I said, yes, so we can use this parity check matrices A and B. And so here when we apply it, yes, so we obtain these syndromes and these syndromes. So I denoted them by V and U. And so what is interesting that these vertical syndromes and these horizontal syndromes, they are dependent. So you have a lot of dependencies between them. And so you can see this if we multiply this syndrome by matrix B and this syndrome by matrix A, in which case you obtain exactly the same, just because you have associativity law, yes, in your field. And so this can be very nicely represented by the following chain complex, yes. So we start from this space, Then we have the second this space that contains these matrices and these matrices. And then we have this space. And here are the maps, yes, boundary maps that we use. And you can easily check that they satisfy this standard property because of this. Okay, it turns out that this chain complex that contains 3 terms, it defines 2 codes. So the first code that corresponds to the second homology, it's exactly this tensor product code. But if we consider first homology, then we define what is usually called hypergraph product code. So here you can see the definition of boundaries and cycles, yes? So this is just these conditions. Okay, and in fact, in order to obtain some meaningful quantum code, so you need to transpose this matrix B, and this is because if you do not do it, so you get the code that has 0 dimension. So if you want non-zero dimension, you need to transpose this matrix, and in this case, this diagram even is much more natural. Yes, so we do not have any transposes here, and so here you can see exactly so the corresponding chain complex. And what is known, and this was shown by Tillich and Zemmer, so they showed that if matrices A and B corresponds to classical DPC codes that has distance d, then using this construction you can obtain quantum LDPC code that has the following parameters. So unfortunately, the distance here, yes, it grows only as square root of the length, as you can see. So, this construction already solves the problem of the rate, but the problem of the distance wasn't solved here. And the natural question, can we generalize this idea to get better codes? And the answer to this question is yes. So we can naturally do this, and here are some main idea. So as I already mentioned before, so the main idea of the classical lifts, yes, when we lift classical codes, that we have also that the distance also grows like linearly with the lift size. And of course the dimension also grows linearly. And if we naturally apply this idea to quantum code, so if we consider the Tanner graph of the quantum code and try to lift it, and if we get the correct quantum LDPC code, then we also have for free linear dimension. And the natural question is whether we also have linear distance. And the answer to the question is positive, so we can do this. And we can do it in a very similar way as we can for classical codes. And so key idea here was that we need to lift so hypergraph product codes. So another way to represent them is just the codes which Tanner graphs are Cartesian products of 2 graphs. So this is another way to define hypergraph product code. Yes, if we take 2 graphs, we can consider Cartesian product, and it exactly corresponds to the construction of hypergraph product code. And here we just generalize this idea, and instead of Cartesian products, we consider lifts of this Cartesian product. Okay, and here, so this main idea described algebraically. So what we do? So we consider exactly hypergraph product codes, but instead of field, we just replace it by the ring. And in fact, this is all you need. So we consider exactly the same chain complex as we had before, yes? And this is absolutely the same formula as we used for hypergraph product code. The only difference that now the elements of the matrices A and B and this matrix W, they are ring, the elements of the ring, and in particular the group ring. So in this case, you obtain a very natural generalization of hypergraph product code And it turns out, so we also have here two types of codes. Classical code that corresponds to this homology, yes, that generalize the standard tensor product code. And it has, it can easily be shown that these codes can be good, asymptotically good. But for quantum code, it is not so easy to show that you can get with this construction asymptotically good code. And in fact, in order to get it, you need high dimensional expanders. So let me go to the next slide. So I also want to briefly mention this particular idea called, which is a very special case of lifted product codes when we apply it not to matrices, but just by one matrices. Yes, A and B are just elements. So in this case, we have a very simple code defined here, yes, with the following chain complex. And if you construct the tenor graph of this code, so you can see a very familiar object, yes, that was used in all recent papers on asymptotically good LDPC codes and also on locally testable codes. So this is exactly the left-right Kelly graph. And these particular codes, they were already studied before. So, for example, Kitaev-Tori code is just special case of this code. But what is also interesting that in the paper by Hastings, it wasn't a paper, so it was his idea that he didn't publish, but it first appeared in 2018. So there's a concept that is called left-right code, and left-right code is just exactly the lifted product code applied to elements A and B, and its parity check matrix is exactly the left-right Kelly graph. Okay. So, and what are expander lifted product codes? So, expander lifted product codes is just lifted product construction applied to two, in general, generalized Zemer codes. So, we can apply it just to standard Zemer codes, but we also can apply it to generalized Zemer codes. So we use two Zemer codes, and we apply lifted product construction, and we get, if we have some special condition that I will describe later, which is kind of analogous to the condition of Sipser and Spielman. So here, so I also use the letter D, so it's like a two-dimensional distance. So in some sense, it's a natural two-dimensional generalization of the standard distance of linear codes. But in this case, so this is a function from, that takes two codes. And if this two-dimensional distance for a pair of codes and their duals also grows at least as a square root of n, then in fact you can get good qLDPC code, and as a bonus, by interpreting this qLDPC code as a LTC, and I'll describe later what this LTC means, you can get also good LTC codes with good soundness. Okay. But in order to understand why we define this kind of, we call it in our paper product expansion, so you need to understand high dimensional expander, because this idea was directly inspired by the idea of high dimensional expanders. Okay. So let me very briefly describe classical LTCs. I assume that in this audience almost all know what it is. So it's just a classical DPC codes where our syndrome also grows linearly, at least linearly, with to the distance of the test vector. Yes, if we have some test vector, we calculate its syndrome, that its syndromes grows at least linearly. And in fact, it grows linearly for LDPC codes. And it is very well known that locally testable codes have very, very redundant parity check matrices, and there is a very good reason for this. And the canonical example is a Hadamard code, and so it's just a set of tables of when we use all possible linear functions and we calculate them at all possible values, and you can easily see that the set of these functions, they all satisfy this linearity condition, and this linearity condition gives you so the length of the code is 2 to the n, but the number of checks here is 2 to the n by 2 to the n, so it's much larger, yes, and which means that these checks, they have a lot of redundancies, and if they have a lot of redundancies, it means that we can define some checks on checks that sometimes are called meta checks. So in this sense, so you can easily see the connection with quantum LDPC codes, because here we have Tanner graphs that consist of 3 parts, yes, and you can see that this, in fact, this also gives you a chain complex. And locally testable codes are very popular because they are used in probabilistically checkable proofs. Okay, and the natural question to ask whether some well-known codes, like, for example, repetition codes, whether they are locally testable. And the answer to this question is it depends. It really depends on the parity check matrix that we use to define this code. So if we use this standard parity check matrix, that so in this case, so we can represent this code as a graph code. Yes, we have bits on edges, yes, and checks on vertices. And you can easily see that this code is not locally testable, yes, because you have this small cut. And this also gives us the idea how to construct repetition code with locally testable parity check matrix. And so here is a very simple idea, is just to use expanders. Yes, so if so we can consider this parity check matrix is just a co-boundary operator of some graph that corresponds to some graph, and if this graph is a good expander, so it means that all these cuts will be large, so you can easily check then this repetition code, it is a locally testable code, yes, and so this expansion parameter that corresponds to the Chigger constant, it exactly corresponds to this soundness parameter for locally testable code. And using this idea, so we can generalize it a little bit, yes, so we can define in a standard way the Chigger constant, yes, so in the Chigger constant is just the best possible parameter eta, and here we can also consider a small set version of this Chigger constant, yes, when we restrict our sets to some small sizes. Okay. And what is a high-dimensional expander? So high-dimensional expander is the idea that was originally motivated by topology, but it found a lot of application in computer science, mostly for local testable codes, first of all. And so here the idea is very simple. So it's just high-dimensional generalization of this co-boundary expansion for graphs. And so if we consider, for example, some simplicial complex or any other high-dimensional object like cubical complex, so we can get almost exactly the same versions of these Chigger constants, yes, and so we can have the standard Chigger constant and also small set version of it. And this small set version, it's kind of corresponds to what is called cosystolic expansion. This is just maybe more modern term for it, I would say, that is often used especially in the context of quantum codes. So here are some very early observations. That the first one was made in the paper by Kaufman and Lubotsky, that large expansion, this high-dimensional expansion, implies large soundness of the code if we interpret this, if we try to use this code as as a locally testable code. Yes, so we can consider this co-boundary operator and interpret it as a parity check matrix, and in this way, so you can have code with large soundness. And in another paper where it wasn't mentioned explicitly, but if you read carefully, you can also see that in the second paper, it was also mentioned that there is relation between this large expansion and distance of the quantum code. And based on this observation, there was a nice paper in 2020 that showed that indeed, yes, you can have, using these ideas, you can have code where dx grows linearly, which was, of course, a great breakthrough at that time. Okay, and so here, let me also briefly mention some four-dimensional analog of this, some kind of hybrid between locally testable code and quantum code. So it is called quantum locally testable code. What it is? So it's a quantum code. So it's a standard quantum LDPC code. But you also require that the checks, X checks and Z checks, are also very redundant. And if you consider the corresponding meta checks, yes, you can consider these two codes, these two chain complexes, and you can assign. So you can consider these three sections and these three sections as a locally testable code. And if this code is if both of these codes are locally testable, then this is called quantum locally testable code. So it's a natural generalization of the ideas of high dimensional quantum LDPC code and locally testable code. And these codes are very interesting in the context of quantum version of the PCP theory. But so before I describe this idea of this high dimensional distance, so let me briefly introduce this very new idea that initially due to work by Dinur and Kaufman, who noticed that you can use sheaves in the context of property testing, and the work by Mishulam that also interpret sheaves on graphs or local systems on graphs as a Tanner codes. And so if we just very naturally generalize this idea, so we get the concept that I call sheaf code. So it's just, what is a sheaf code? So if you have some cell poset, so if you have some, for example, simplicial cubical complex, you can consider it cell poset. And if X, so if here it is the set of maximal elements, and here is the maximal elements that contain, so this is the maximal cells that contain some particular cell, and so you can interpret this cell poset as a topological space, because every poset is an Alexandrov topological space, as if we consider if open sets are our upper sets of this poset. And so we can define a sheaf on this topological space. And so in very simple terms, so this sheaf, it's just a Tanner code. It's a Tanner code that is defined. So it's a generalization of Tanner code where you have not just one level of checks, but you also have like several levels of checks, and that are ordered by dimension. So you have trivial checks that correspond just to bits. Then you have higher order checks, and so these checks are ordered by codimension. And you can consider the standard Tanner codes as sheaves on graphs in this way. Okay, and so here the Zemer code that I already mentioned before, interpreted as sheaf codes. So it's so here we have two levels. So these trivial codes and these local codes, yes, in the standard Tanner construction. But if we consider classical code that can be obtained from our quantum LDPC codes, and we obtain a code that is almost exactly the same as a famous code invented by Dinur and her co-authors in 2021. That was the first example of good locally testable code with good soundness. So in this code, if we also require this property that I call two-dimensional distance, and if it grows at least a square root of n, so this is not what was shown in all that papers. I just try to summarize and just conceptualize what was shown. And you also get kind of two-dimensional analog of Sipser-Spielman code. And in this case, so you have 3 levels. Yes, so you have local code that corresponds to bits. You have horizontal and vertical lines, and you also have like squares. Yes, and these local codes are product codes. Okay, and this is of course an example of a sheaf code, but in this case the sheaf is defined on a square complex, this left-right complex. Okay, and so finally, so I have so we're not so far from the end. So the natural question is, what is this high-dimensional distance? Yes. So as I said earlier, so this is an idea that was inspired by the theory of high-dimensional expander, and the answer is very simple. So when we learn about this idea of high-dimensional expander and how you get in these papers in 2014, yes, how you can get locally testable codes and quantum LDPC codes from them. So we notice that in order to have a good high-dimensional expander, you need to make sure that in your links you have expansion. You have very good expansion. And so the key idea was what is the natural analog of this expansion? Yes, if we consider it's on this kind of sheaf codes. And the natural analog is just the compounded expansion if we interpret product code as a graph code. So so every product code, it was already mentioned, noticed by Tanner, can be interpreted as a graph code. Yes. So we have a graph, and so here, for example, our columns, and here, for example, our rows. Yes, and this Tanner graph, it defines exactly the tensor product code, and we can consider this Tanner code using this idea of Mishulam as a local system on this graph, and this way you can naturally extend the idea of co-boundary expansion to these local systems. Yes, and so you just apply exactly the same formula, and you get the co-boundary expansion. And so this distance that I mentioned here, so it corresponds to, so in high-dimensional case we have many levels. So for the product of 2 codes, yes, we have not so many levels. It's not very interesting. But if we consider the tensor product of many codes, then we have chain complex that corresponds to this tensor product code, and this chain complex is just a tensor product of the corresponding chain of the chain complex as shown here. And if we interpret it as a sheaf on some simplicial complex, so we can define Chigger constants. And it turns out that this last Chigger constant is the most important one. So if we have good Chigger constants here, so then you can show that you also have good Chigger constants for all other levels. And so this exactly corresponds to this idea of high-dimensional distance. So this high-dimensional distance just means that we have good expansion in this high-dimensional expansion in this chain complex that corresponds to tensor product code. And so here, so my final slide. So it's So as I said, so it is also interesting to apply these ideas to construct good quantum locally testable codes. And it turns out so we can obtain something similar for quantum locally testable codes if we use a natural generalization of the previous construction to higher dimensions, in particular to 4 dimensions. And what we showed in our very recent paper, that you can have this very large high dimensional distance, and you can have it for both for codes and for their duals. And as it turns out, so this idea can be used, already used now to construct almost good quantum locally testable code. And by almost good, I mean that this quantum locally testable code that has almost good parameters. So their distance is almost good, yes. And so as far as I remember, soundness also, yes? Okay. And you can also, there are also another couple of papers that already use this idea to construct some other codes. And so the key proof idea here was quite unexpected. So it turns out, so here that you can need to consider some codes that we called maximally extendable product codes. And this is something that is very related to the Schiff interpretation. Because in Schiff theory, we have this problem of extending, yes, from local sections to global sections. And if we consider this product code as a Schiff on simplicial complex, yes, if we say that, and we say that the code is maximally extendable, if whenever it is extendable in some other product code, it should be extendable in our code. So we call this maximally extendable code, product code. And if our product code has this property, then it turns out that this gives you exactly what we need to get these codes of very large high dimensional distance. Okay, thank you for your attention. Yeah, exactly. So for sufficiently large Q, so in here we use, in fact, our hope was to replace this not very familiar object called maximally extendable product codes with much more familiar codes that were studied previously. Yes, they are called maximally recoverable codes. So they are often used in the context of data storage, and this is very similar, but it seems that different idea that so the code is called maximally recoverable if it can correct all possible erasures that other codes with the same parameters can. Yes, so if we consider, for example, a product of two codes with some fixed dimension, and the code is called maximally recoverable, yes, if it can recover all possible erasures that all the codes from this family can recover. And this idea of extendability is in fact very similar to this idea of recoverability. So it's almost the same, but there is a slight difference, and so currently we are not sure that this is exactly the same. So in our hope, of course, is that this is exactly the same, but we haven't proved it yet.
So what is missing for getting good quantum LDPC code?
Okay, that's an excellent question. So what is missing? So here, so we have the following problem. So we have, from the one point of view, so we have a very general construction that kind of a generalization of a lifted product code that can work with arbitrary local codes, yes? You do not need to place any restrictions on these codes if you want to use it. But if you want to use, for example, cubical or Ramanujan complexes, which I suppose you mean here. So in this case, you need to use local code that has some symmetry, that corresponds to local symmetries of these cubical complexes. So in that case, in fact, it is possible, it is still possible to generalize these ideas to these Ramanujan cubical complexes. But the problem is that you need to have codes with some very specific symmetries. And so usually it's just symmetry of projective line, because yes, locally they have these projective lines, and this is unknown whether such codes with these symmetries exist. So if they exist, then yes, I suppose yes, we already can construct good qLTC codes.
Like the vector space, say F2 to the projective line.
Yeah.
You have to find a subspace.
Yeah.
Invariant under
Yeah, invariant codes, yes.
they have the good properties.
Yeah, if they have the same properties as we shown here, then yes, using for example, the proof by Dinur and all, so you can just construct good qLTC codes.